through an example where we find the length of a rectifiable curve on a closed interval. Now remember, the formula from calculus to find the length of a curve is s is equal to the integral from a to b of the square root of 1 plus f prime of x squared dx. If you have a function y equal an expression in x's, or your function f of x equal an expression of x's, or you could have s is equal to the integral from c to d of the square root of 1 plus f prime of y squared dy. If you have an expression x equal a function in y's, or f of y equal an expression in y's. So for these you could do either instance. For the closed interval, when you have it, a function f of x is equal an expression in x's, it's over the closed interval along your x coordinates of your closed interval. And then if it's in terms of y's, it would be the y coordinates of your closed interval, the y at the start and then the y at the end. So those are the two formulas that you would have. Now our example, we have a function f of x equal an expression of x's on our interval of x's. So for ours, we're going to use this first formula. Now, this function, 3 halves x to the 2/3 plus 7, is a continuous function. When I find its derivative is continuous on that interval. So it is a rectifiable curve, and we'll be able to go through and find the length. So remember, a rectifiable curve means a curve that has a finite length. Now our formula involves the derivative of the function. So if our function f of x is 3 halves x to the 2/3 plus 7, then our derivative f prime of x is, well, taking the derivative of letter base to number power, bring the exponent down, multiply it to the coefficient that's in front of it, and subtract 1 from the exponent. Well, if I bring 2/3 down and multiply it to 3 halves, that just gives me a coefficient of 1. X to the, subtract 1 from 2/3 and you get a negative 1/3. And then the derivative of the constant term 7 is 0. So that's just our derivative. So our arc length is the integral from 1 to 8 of our square root 1 plus this x to the negative 1/3 squared dx. Now this derivative, f prime of x is x to the negative 1/3. That's 1 over x to the 1/3 power. So that's 1 over the cubed root of x. The only place that's undefined is at x equals 0. And our interval goes from 1 to 8. 0 is not in our interval. So our derivative is continuous throughout the interval that they want us to find the length of the curve. Now when I'm looking at integrating this, remember, if you have a variable expression yet to another power, you keep the base and you multiply the exponents. So negative 1/3 multiplied to 2 over 1 would give me a negative 2/3. So that's x to the negative 2/3 in that term in the radical. Now I can't do a u substitution the way it is written right now, because if I pick that as u, the du would have a variable component factor to it, and I don't have any variable factors outside the radical. So what I'm going to need to do is simplify this a bit before I'm actually able to go and integrate it. Now remember, a negative exponent means 1 over the expression with the positive exponent. So we're going to at least try to do that. At this point, we're just trying to figure out how simplifications might get us someplace that we can integrate it. So this will be 1 plus 1 over x to the now positive 2/3 power in the denominator in that term. Still not able to integrate it this way. But there is an addition of 2 different terms in the radical. So let's build to get common denominators and put these 2 terms together. So my lowest common denominator is going to be x to the 2/3. So I'm going to build this 1 by x to the 2/3 over x to the 2/3. So that'll be an x to the 2/3 over x to the 2/3. to get your common denominator. Now add your numerators together and keep that common denominator. That gives me s is equal to the integral from 1 to 8 of the square root of x to the 2/3 plus 1 all over x to the 2/3, all under the radical, and then dx. So I just got the common denominator, added the numerator, kept the common denominator. Now, in a quotient, I can break up the radical of the numerator and the radical of the denominator. So that'll be the square root of x to the 2/3 plus 1 over the square root of x to the 2/3, and that's dx. And you can't break a radical up over additions or subtractions. It does not give you the same thing. So there's nothing really that I can do with that numerator. In the denominator, the square root of x to the 2/3, well, remember, square root is like an exponent of 1/2. And if I take x to the 2/3 to the 1/2 power, exponential expressions to yet another power, you keep the base and multiply the exponents. The common factors of 2's would remove, and you would get just x to the 1/3 in the denominator. Now if I have an x to the 1/3 in the denominator and I bring it up out of the denominator into the numerator, that becomes an x to the negative 1/3 out of the denominator. I'm finally at a point here where I can do u substitutions to integrate this. So let u be the part of that integram that's being acted on. So we're going to let u equal the x to the 2/3 plus 1 because it's the square root's acting on that. So if u is x to the 2/3 plus 1, and I calculate what du's replacement would be with that u substitution. Remember, don't look back at the process here. Look what you said u was equal to, and then find the differential du. And the derivative of x to the 2/3 is 2/3 x to the negative 1/3. The derivative of 1 is 0, and then the differential then gives me the dx. So when I look back over here, I've got the x to the negative 1/3. I have the dx. The only part that I don't have is a 2/3. Now we can handle this one of two ways. I could either divide both sides of this by 2/3 so I get the replacement, or I can put a 2/3 here so that it matches that, and then compensate by multiplying by a 3/2 outside the integral, because 2/3 times 3/2 is just 1, so I haven't really changed the expression. I'm going to divide both sides of this by 2/3, and when you divide by a fraction, you multiply by the reciprocal, so that would give me 3/2 du is equal to x to the negative 1/3 dx. Okay, now we're going to make our replacements. So s is equal to the integral x equal 1 to x equal 8. I'm going to write it that way so I remember those are the x values, not the u values. U is x to the 2/3 plus 1. So this expression is u. So I have the square root of u. And then x to the negative 1/3 dx, its replacement is 3/2 du. So when I take that out, its direct substitution in expression in u's is 3/2 du. So replacing this, I'm going to take that out and put in the 3/2 du. So now we can factor that numerical factor out in front of the integral and look at that as x equal 1 to x equal 8 of u to the 1/2 du. And now that's something that I can integrate. Letter base to number power, add 1 to the exponent and divide by that. So I have the 3/2 that was already out. Now add 1 to 1/2, I get 3/2. When I divide by 3/2, I'm multiplying by 2/3. U to the 3/2 power. And I'm evaluating that from x equal 1 to x equal 8. You can go one of two ways here. You can switch your x coordinates over to their expression in u's and plug it in. Or you can go back to x's, make your replacement back to the x to the 2/3 plus 1 that is being raised to the 3/2 power, and then plug in the 8 and the 1. I'm going to switch these over to u's. So if x is 1, 1 to the 2/3 power is still 1. 1 plus 1 is 2. So then x equal 1 changes to u equal 2. If x equals 8, 8 to the 2/3. Remember, the denominator of the fractional exponent is the root and the numerator is the power. So 8 to the 2/3 would be the cubed root of 8, which is 2, squared, which is 4. And then 4 plus 1 gives me 5. So now I can look at this expression and plug in the values. The 3/2 times 2/3, that's just 1. And I've transitioned these values to u's. So that's 5 to the 3/2 minus, plug in the 2, 2 to the 3/2. And remember, that means 5 to the 3/2 power is the square root of 5 cubed. Well, if I have the square root of 5 cubed, I can bring a factor of 5 out. So think about it this way. It's the square root of 5 cubed minus the square root of 2 cubed. So I can bring a 5 out. So that's 5 times the square root of 5 minus, I can bring a 2 out, 2 times the square root of 2. So 5 times the square root of 5 minus 2 times the square root of 2 is the length of this curve on the interval from 1 to 8. That's the exact simplified length of the curve, and that's about 8.352 units long if you go to an approximation. But generally, we like to have the exact value of it. And if you want to report the approximation as well, but not as a replacement as well, it's about 8.3